Okay, percent composition and empirical formulas. So these are two very related concepts. They have to do with the composition of compounds and describing how different elements make up a compound. So percent composition is really a ratio of masses. It tells you what percent in terms of the mass is a compound of different elements. So in the example, the simple example given here, 10% is listed for element A and 90% is listed as element B. And what that means is out of any given mass, 10% of the mass or the grams will come from A and 90% will come from B in terms of their atoms. And so you can translate that into actual gram amounts, 10 grams and 90 grams out of 100. You could have also written 1 gram for every 9 grams, A versus B. So a percent composition, or when you're given that information, it's giving you information about a ratio of masses for the elements in a compound. So an empirical formula, on the other hand, gives you the lowest whole number ratio of the atoms of elements in a compound. Or you can just think of it as the lowest whole number ratio of elements in a compound. So this same compound that we were talking about on the left could, even though it's a 1:9 mass ratio, it could be that it's actually only a 1:2 atom ratio, because the different atoms of the different elements have different masses. So in this example, if A had a relative atomic mass, as we call it, or a molar mass of 10, and if B had a molar mass of 45, then because they don't weigh the same, because B is a lot heavier, if the chemical formula, or the empirical formula, which is what we're talking about right now, is AB2, so that implies there's 1 atom of A for every 2 atoms of B, then the A weighs 10 grams, and then we have 2 B's, so we have 2 times 45 grams. So we have 10 grams of A, and we have 90 grams of B. So even though there were only 2 atoms of B, twice as many atoms of B, there's a lot more mass from B because the B atoms are heavier. And so now 10 grams A, 90 grams B, we would have, if we talked about percent by mass, 10% of this compound is A and 90% of this compound is B. So percent composition and empirical formulas are very closely linked, and they often show up in questions together. Typically, you start with the percent composition information, which is information about mass, and you convert it to an empirical formula, which gives you a ratio of the atoms or the moles of elements in a compound. So here's an example where we actually use a real chemical formula. So carbon monoxide is CO, is its chemical formula. That's its empirical formula, it's its molecular formula. So actually, every molecule of carbon monoxide is just 1 carbon and 1 oxygen. And so it's a ratio of 1 atom of carbon bonded to 1 atom of oxygen. Okay, if we want to determine the percent composition, as this first example is asking us to do, then we're going to look at the periodic table, and we're going to find the relative atomic mass of each element. Carbon's relative atomic mass on the periodic table is 12.01, and oxygen's is 16.00. Now in the formula, CO, even though they're not written, it's implied, because they're not written, that there's 1 carbon for 1 oxygen. So I multiply the atomic mass by the number of atoms in the empirical formula. So 1 atom of carbon times 12.01, that gives me 12.01 mass. I can think of it as grams if I'd like. 12.01 grams from carbon, and 1 times 16 gives me 16 grams from the oxygen. And that means the total molecular mass, or molar mass, of carbon monoxide is 28.01. And we would say, if we use grams, we would say that is the mass That is the grams per mole. Okay? If we don't use grams and moles, then we would call it the molecular mass, the mass of a molecule, a single molecule. So if I want to determine the actual percent by mass for each element, any percentage is you're looking at the part divided by the whole. So to determine the percent that is carbon, I take the mass, 12.01 of carbon. Now it's 12.01 because there's only one carbon in this example. Okay, so the mass from the periodic table is 12.01, and there's one of it, so that's why it's 12.01 on top. And I divide that by the mass of the whole empirical formula, which was 28.01, times 100% to turn it into a percent, and this compound is 42.88% carbon by mass. So all the grams that are in a sample of carbon monoxide, 42.88% of those grams are coming from the carbon atoms, and by process of elimination, or by repeating that process, we would know that the other 57.12% are coming from the oxygen atoms. Okay, let's do another example. I'm going to stick with an example that has carbon and hydrogen and now has oxygen. So the difference in this example is, again, I'm finding their relative atomic masses on the periodic table. So when I look up and I find carbon, in addition to telling me that carbon is atomic number 6, there's also going to be a mass, a relative atomic mass there. So that's where I'm finding these, on the periodic table. And then I'm multiplying by the number of atoms that are in that formula. So there were 2 carbon atoms here in ethanol, so I multiply it by 2 and I get 24.02. So I follow through for all the different elements and I get the total molecular mass or molar mass. And then to get the percent composition for each element, notice this time for carbon, I didn't use 12.01, I used 24.02 because there were 2 carbons, so I had to go back up here. What's the total mass from carbon? It was 2 times 12.01, or 24.02. I divide it by the whole mass times 100. And so in ethanol, 52.13% comes from carbon. If I repeat the process, I find out that 13.15% comes from hydrogen and 34.72% comes from oxygen. So I can break down now by mass how much each element is contributing. And you can see that even though hydrogen has the most atoms of any of the different elements, it makes up the smallest percentage of the mass because it's the lightest element. Okay, really quickly, if we now flip this, right, we're trying to figure out the empirical formulas. So I have, this is the first example. We figured out that in carbon monoxide, carbon was 42.88%, and the other one was 57.12% of oxygen. Remember that that's a ratio of mass, so I can pick any masses I want so long as they follow that ratio, and I can treat it as though I have those masses, because I'm just trying to go from the ratio of mass to the ratio of atoms. So the easiest way to do that is to say, well, if I have 42.88% carbon, then if I had 100 grams, I'd have 42.88 grams of carbon, 57.12 grams of oxygen. Or you can do it in atomic mass units. Let's stick with grams. And then the trick there is to figure out, okay, if those are the gram amounts that I have of carbon and oxygen, how many moles is that? The way that we convert into moles is we say, well, 42.88 grams of carbon, and it's 12.01, that same mass from the periodic table, grams per mole for carbon. And if I do that division, I get 3.570 moles of carbon atoms. I've done it down here just in atoms, but we can also think of it as moles of carbon atoms. If I repeat the process for oxygen, then I do 57, whoa, where'd I go? There we go. If I repeat the process and I say 57.12 grams of oxygen divided by 16 grams per mole for each oxygen, I also get 3.570 moles of oxygen. And because the number of moles are the same, 3.57 to 3.57, that's a 1-to-1 ratio. So 1 carbon mole for every 1 oxygen mole. And therefore, that means the ratio of atoms, 1 carbon atom for 1 oxygen atom, And so the formula is CO for the empirical formula, the lowest ratio of moles.